Continuing the theme of monitoring, reporting, and verifying, we need to be sure as well about how to measure the carbon fluxes from the various land use sectors. We have seen this from the at the beginning of the course, looking at historic emissions in terms of sources and sinks. We had fossil fuel carbon obviously being the biggest source, with land use contributing. As a fraction of the total emission, land use is decreasing, but it continues to be a positive source. In the meantime, ocean fortunately continues to take up more carbon as the atmospheric concentration increases, and land continues to take more as well. And atmosphere is of course accumulating a lot at some 4 ppm per year, which is bad news, especially in the sense that despite all these years of negotiation, the emissions are not actually showing any reductions. And the accidental reduction that happened because of the COVID lockdowns actually didn't give us immediate cooling, because obviously CO2 accumulates and has a long residence time. So the CO2 we have already emitted over the last several decades and a couple of centuries are continuing the warming. So 2020 turned out to be the warmest year, tying the record with 2016. We have already talked about the residuals that are now attributed to terrestrial sinks. Some people don't like calling it a missing sink, but some people still use that terminology. Nonetheless, land is fortunately still a net sink. So this is looking at the same thing in a slightly different way for particular averaged emissions. So these are CO2 equivalent fluxes now in petagram carbon per year. So you have to get comfortable with these units that we keep switching between a gigaton carbon or gigaton CO2 and then petagrams carbon or petagrams CO2 equivalent, and so on and so forth. Okay, so fossil fuels, positive source. Land use, we have the gross source land use as a gross sink, and the net land use change is contributing this amount here. Atmospheric growth, obviously that means you can think of atmosphere as a sink, right? It's accumulating carbon, and compared to the overall budget, that means it's keeping it in the atmosphere, which we feel directly. So it's slightly counterintuitive to think of it as a sink. Nonetheless, ocean has a sink because it's accumulating carbon. That's why these are both sinks. And land is accumulating CO2 as well. So here you're looking at CO2 equivalent fluxes for methane, CO2, and N2O. You can see both of them shown here as well from multiple sources, and these are in petagram carbon and petagram CO2. So you can see that 3.7 multiplication factor here. So main point in this context is that land still continues to be a sink, which brings us to ways of estimating land fluxes. So remember, I hope it's clear by now that you need the fluxes, the exchanges, as well as the stocks, what is sequestered in trees, land, soil, surface soil, deep soil, and so on. Okay, so Earth system models set up including land use feedbacks as one way of measuring the exchanges, and they can be done with and without land use and land change simulations, disregarding fossil fuels. So in the models you can take things out and in to see how the feedbacks actually work. You can do single, coupled, or uncoupled simulations. So you can just focus on one particular land use change, like let's say deforestation. So this is including fossil fuels. There are sensitivities studies that are done to do this, but I'm just using this as an example to tell you how the land use, how the land fluxes are computed. We have already talked about the uncertainties in the carbon cycle, but this is the best we can do. Inventory-based bookkeeping tend to be bottom-up, so they look at the various boxes into which carbon stock exists, and then carbon gradients exist and carbon fluxes exist, right? So if you think about air C CO2 flux, for example, it depends on the difference in the partial pressure of CO2 in the water at the surface and in the air, and some additional factors like wind speeds as a cube of the wind speed, and there is some non-dimensional numbers like Schmidt number and so on, which look at the stability and the drivers of gas exchange. Same thing happens on land as well. So these are uncoupled dynamic global vegetation model simulations and transient simulations. So transient simulation basically means, let's say you start at the Industrial Revolution, you continuously prescribe vegetation, land use changes, CO2 in the atmosphere changes, volcanic forces, surface solar energy output changes, and then you integrate forward and you can look at year by year change. Whereas the simulations which only look at a certain period, let's say you want to only compare 1990s and 2000, then you somehow initialize the model at 1989, you integrate to 1990, and then you integrate over 2000s and you compare those two. Those are not necessarily transient simulation. Or for future projections, you may want to only look at the 2050s or 2080s and not go continuously integrate from let's say 2021 to 2050, because these transient simulations can be very expensive, especially when you include all the details like dynamic global vegetation model and so on. So those are equilibrium simulations. Okay. Just to repeat the point, the emissions in terms of here milligram CO2 equivalent per meter squared per hectare, completely different unit because these are local flux measurements. They are not global or averaged over large areas. And looking at CO2, methane, N2O, and total CO2 equivalent, converting the way we did before. The main point here is that the land use type, forest, grassland, barren, cropland, wetland, they determine which is the dominant greenhouse gas that's coming out of these land use types. Okay, so you can see that some are pretty close to zero in terms of methane from forests, grasslands, but it's higher for wetlands. But you can also not miss the fact that the uncertainties here are quite high. So not only are the models uncertain, or they have uncertainties, but even the measurements are not so easy. And if you want to do a whole wetland and you measure it in one or two spots, you have to know how variable spatially the fluxes are. Very, very complicated story, right? Nonetheless, typical total carbon stock changes in million kilograms carbon per kilometer squares when converting to croplands in terms of above and below ground carbon from set-aside temperate grasslands, temperate forests, tropical grasslands, and tropical forests. I already showed this, and you can see that there are really not many good news stories here. You always lose carbon when you do that. Only the tropical grassland to palm oil here shows additional sequestration, because the grasslands are not very high carbon sequestering type of vegetation. On the other hand, palm oil contribution to global warming is increasing in terms of million tons of CO2 equivalent emitted per year, and here is the share of global CO2 equivalent emissions from palm oil. The two curves are shown here, which means, again, life cycle analysis is needed to make sure that the critical issue of competition for let's say forest versus palm oil actually provides climate mitigation. This is very critical and always not easily guaranteed. There is aggressive push for conversion, as I said, let's say using El Nino forecasts to set fire to clear forest lands, if it's happening. There is some evidence that it does. That's because palm oil is it's a cash crop. You make a lot of money out of it. So this is where the ecosystem service concepts become complicated. A forest has a lot of ecosystem services. Theoretically, you can compute it in terms of food, fiber, medicine, cultural value, uh, sequestering carbon and other co-benefits in terms of water quality, air quality, etc. But how do you pay to protect that forest while the motivation to cut it down, grow palm oil, and make money is so high, right? So that's the human dimension of critical issues for land as a mitigation sector in for climate change, right? So those have to go into the life cycle analysis as well, right? Profit motive. Can it be done without driving up overall carbon emission or reducing carbon stocks?